Welcome back to Advent of Code 2021. Day 19. Alright. Yeah, just a few days left. One whole week. Beacon scanner. Oh yeah, so this one, look, we took a peek last time. It looks like a geometric kind of problem. As your probe drifted down through this area, it released an assortment of beacons and scanners into the water. It's difficult to navigate in the pitch black open. I'm going to skip ahead a bit. Each scanner is capable of detecting all beacons in a large cube centered on the scanner. Beacons that are at most 1,000 units away from the scanner in each of the three axes have their precise position determined relative to the scanner. 1,000 width, 2,000 width cube. It's actually 2001 width cube, but you just think of it as 1,000 away from the center. Wherever scanners cannot detect other scanners. Alright, so we've got some input is wait, what? Okay, so we've got a list of beacons that each scanner can detect. I guess. Okay. So if it's at that coordinates and there are beacons there and there, then the scanner could report that the first beacon is at that relative to the scanner, but would not detect the second beacon at all. Alright. Unfortunately, while each scanner can report the positions of all detected beacons relative to itself, the scanners do not know their own position. You need to determine the position of the beacons and scanners yourself. The scanners and beacons map a single contiguous 3D region. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions, such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other, allowing you to reconstruct the beacon map one scanner at a time. Alright, but I thought these beacons are given as relative coordinates, not global coordinates, universal coordinates, whatever. Well, we'll read on. Alright, so in 2 dimensions, we have this. The scanner O sees it like this. Okay. That's what scanner O sees. Scanner 1 sees that, fine. Relative coordinates. For this example, assume scanners only need 3 overlapping beacons. Then the beacons visible to both scanners overlap to produce the following complete map. Oh, these are the same beacon? Okay, that would make things a lot clearer. They're all talking about the same... Oh no. No, they wouldn't, because some beacons are not visible. So it's not necessarily... What is it asking now? Not sure yet, but... They're not really saying what these lines are. Let me look at that again. The submarine has automatically summarized the relative positions of beacons detected by each scanner. Okay. So it's arbitrary beacons. It's not necessarily the same beacons. So in this example... Is that... Oh, 1 hour, wow, okay. Is that the longest yet? So this is implying that, well, okay, assume scanners only need 3 overlapping beacons. then the beacons visible to both scanners overlap to produce the following complete map. I don't understand this assumption. Like, you only need 3 overlapping beacons in order to... I mean, are they saying that every pair of scanners have 12 beacons in common? I don't really understand this paragraph. If we knew that these 2 scanners had 3 beacons in common, then we would know that those are the same beacons. And not necessarily in order. So that one is not... Yeah, so the order isn't the same, but the shape... Yeah, okay, if we knew that they had 3 in common... I don't really understand that assumption, though. That doesn't immediately seem to fall out of that paragraph there. It says... finding pairs of scanners that have overlapping regions, but we don't know... Okay, read on. Find the common beacons first. But that's impossible. Like, it's all relative. Like, for all we know, these could be... like, a long way away from each other, so that there's 0 overlapping. Unless there's more stipulations, but unfortunately, there's a second problem. The scanners also don't know their rotation or facing direction. Due to magnetic alignment, each scanner is rotated some integer number of 90-degree turns around all of the X, Y, and Z axes. That is, one scanner might call a direction positive X, while another scanner might call that direction negative Y. 2 scanners might agree on which direction is positive X. One scanner might be upside down from the perspective of the other scanner. Okay. So it could be in any of 24 different orientations. There's 6 different facings. And for each of them, there are 3 different axes that consider the up direction. We used to have to respect, like, what was it? The left-hand rule? The right-hand rule? I forget now. There's one for one thing and one for another thing, which... Well, alright. Here is an arrangement of beacons as seen from a scanner in the same position but in different orientations. Okay, so basically the axes are shuffled. By finding pairs of scanners that both see at least 12 of the same beacons, you can assemble the entire map. For example, considering the following report. Because all coordinates are relative, in this example, all absolute positions will be expressed relative to scanner 0. Scanners 0 and 1 have overlapping detection cubes. Why? The 12 beacons they both detect are at the following coordinates. What? Just compare if they share 12 values. I still don't understand. Are they asserting that they do share 12 values? Then that's knowledge we know. Or are you trying to find if they share 12 values? Because if it's the latter, that's still impossible because it's relative positions, not absolute positions. The 12 beacons they both detect are at the following coordinates. -618. So -618 was relative to scanner 0, so it should appear in this list. What? Well, I don't see a -618. At the following coordinates. I don't see these in scanner 0's. So we're taking absolute here to mean relative to scanner 0. I guess with distance matrices. This is poorly explained. I don't think it's... This paragraph is the most confusing one. These examples don't... Right, if we go back to the simplest 2D example... Assume scanners only need 3 overlapping beacons. Hang on, so... Yeah, still, these don't appear. Okay, 618, did it appear in the other axes? Maybe it was a different axis. Okay. Oh, it was there, I didn't see it. Okay, it is actually there. -618, -824, -621. Okay, fine. So those are actually in scanner 0's set. All beacons they both detect are at the following coordinates. So it's minus... Where you could compare Manhattan distances with each scanner. So it shouldn't. 618. I wouldn't expect to find it in scanner 1 because it's like not relative. So let me just check if it's actually there. No. Okay, fine. So alright, so they seem to be establishing that it's a fact that every pair of scanners has at least 12 beacons in common. If that's true, then I guess there is some... Okay, fine. Then I guess you can deduce by some process that it must be these 12. I'm not sure how yet, but I guess that's the part of the problem. Like, and then if you knew... Okay, so let's assume we knew how to do that. I don't think every pair of scanners has 12. But you have to find the ones that do. What? So they either do or they don't? And then we know nothing. I'm so confused now. Then we have absolutely nothing in common between these scanners. Like, how can we possibly know whether whether a beacon is the same in one than the other? Like, they could be like a million spaces away from each other. Check the small example. I mean, the small example, this could be in one region of space, and this could be in a completely other region of space. They could be completely separate beacons. Or they could be in the same space, and they'd be the same beacons. Like, I don't see any information that can tell us whether they're the same beacons or different beacons. I don't understand how this falls through. Like, why is it necessarily the case that these... It's telling you how it works? I mean, did they tell us how many beacons there are? If we knew how many beacons there were, maybe we could narrow it down. Yeah, I don't even get the small example. Like, what? There are an unknown number of beacons in existence. Scanner 0 sees 3 of them. Scanner 1 sees 3 of them. So we know there's a minimum of 3 beacons in existence. And it's a maximum of, well, unlimited, because there could be others that they can't see because they're further away. So given just that information alone, that's all we know. Assume scanners only need 3 overlapping beacons. Finding pairs of scanners that have overlapping detection regions. So how do we find... Okay, we know there's only 2 scanners in existence in this example. So it says we're trying to find pairs of scanners that have overlapping detection regions. Are they basically saying there definitely exists at least one such pair? But they're not actually saying that. What you have to find is matching distances between beacons, if I'm not misunderstanding. Yeah. I mean, that's if we know that two scanners have beacons in common. X number of beacons in common. I still don't understand which pairs of scanners have beacons in common, and which, like, does every single pair of scanners have 12 beacons in common? Is that what they're saying? All scanners are mapping the same region. Yeah, but they don't cover the whole region. No individual scanner covers the whole region. So they could all be close together and have a lot of overlap, or they could be far apart and have very little overlap. Ah. So they say it's contiguous. That means scanners are necessarily connected. Like, every scanner is gonna overlap with at least one other scanner. Okay, that's probably true, but they could be in a line and just touching, their regions are just touching. So they could be in a line, or they could be kind of all clumped together. Could even be in a donut shape with a big hole in the middle. Or you could find the ones that have 66 matching distances between beacons. 12 choose 2. But even if there are matching distances, it doesn't mean... Like, it could just be that there are a bunch of beacons that have some pattern of matching distances between them. And that exact pattern happens to be seen elsewhere. So it doesn't mean they're the same beacons, does it? Like, like, in the most extreme example, if we're assuming they have to be contiguous... Yeah, I mean, it's possible for these regions to be contiguous, but no beacons overlapping whatsoever. That's also possible. You literally just line up the cubes next to each other and just have each of these literally the cubes are just touching on the corners or something, or just on the edges. So each of these could be completely separate beacons, and no two are common. No two are the same. That would technically meet the specifications here, I would think. Like, I don't see anything that prevents that from being the case. Ideally, you'll find a lot more than 66, so you'll be sure that more than 12, since you don't care about the exact number of matches. Like, okay, this example. Okay, this sentence here. Scanners 0 and 1 have overlapping detection cubes. Where does that come from? How do they know that? Like, they said it's contiguous region, but that doesn't mean 0 and 1 are connected. It could mean 0 is connected to 3 and 3 is connected to 1, like in a line. So what led them to believe that scanners 0 and 1 have overlapping detection cubes? And then it says scanner 4 overlaps with scanner 1. Why 4? Why have they jumped to 4 now? What happened to 2 and 3? I don't know, none of this makes any sense. 2 and 3 don't share 12 beacons with the others. Why? How do we know any of them share any with any? I don't get where they got the first sentence from. Like, these are just arbitrary numbers. Why is it any more likely that 0 and 1 have common beacons than 1 and 2 or 2 and 3? That's what you have to figure out. Well, I don't think it's possible, according to my understanding. Like, these... Like, according to the description, these could be cubes that are just next to each other. And these could all be beacons within those cubes, respectively. So I would think that these could be completely different beacons, none of them coinciding, and it would still meet the description, wouldn't it? Like, they didn't say anything about how many they must have in common or anything, they just... So I would think it's possible to have 0 matching beacons, and that's a valid layout of these coordinates. But are they just like... They're just choosing 0 and 1 to have overlap? But they wouldn't have given you an input like that. But no, I'm saying for this input right here, these could be separate cubes. Like, what, it's just, they're all relative coordinates. Why? How is that any less likely than showing you the exact coordinates that match after that? But, what, this? But these don't match, because let's say that triplet there, that's in scanner 0, because they've decided scanner 0 is the origin. But that's not in scanner 1. (618) matches with 686. Yeah, but we could say this matches with, like, that one. Or we... Well, okay, no, that wouldn't work, because then the others wouldn't match up. But we could say that it doesn't match with 686. Like, we could say that they literally don't match up at all. I don't get where they got this sentence from. Like, what's stopping scanner 0 and scanner 1 from being, like, I don't know, 5,000 units apart, and none of these actually match? Basically, it's a single cube with 79 beacons. But they didn't say... They didn't tell us how many beacons there were. All we know is the minimum at the end. Yeah, but that's not in the input. How can they deduce that? Like, the minimum number of beacons must be... say, this number of rows. Or, I don't know, I guess whatever the most number of rows is on any one of these scanners. It tells you it's 79 always, does it? Oh, that changes things. Where does it say that? beacons. Total there are 79 beacons. Oh, I thought this is for the example. Wait, is it? Yeah, no, they're saying that's the conclusion of the example, yeah. Not. Yes, that's the conclusion, but I mean, I don't get it. I could argue that I could say that every single one of these beacons is unique. In which case the number of beacons is that number plus that number plus that number, that number, it's that number, which is more than 79. Like, what's stopping that from being a valid interpretation? Hmm. How many are there anyway? Okay, so what's... And this number 12, what's special about 12? They're saying if you knew that a pair of scanners had 12 beacons in common, then you would be able to work out. Start with the example input and try things until you get 79 as a result. But still, I mean, I just gave... Like, I just gave an interpretation where 79 wasn't the result. I'm just trying to figure out why that interpretation is wrong. I still can't find any reason why it'd be wrong. Like... Why can't these all be completely distinct? What is the factor that's stopping them from being distinct? They said something... They said this thing about 12. I still don't fully understand this paragraph. But nothing in this paragraph is saying there must be any overlap at all. They just say find pairs of scanners that have overlapping detection. Okay, so they're asserting that... I think they are implying that there must at least exist at least one pair that has at least 12 beacons in common. Maybe that in itself is an important piece of information. They don't actually say that, but okay, so we'll assume there exists at least one pair with 12 beacons in common. Is that enough information to then for everything to fall out? Maybe. So if we know that there's these 4 scanners, and we know some pair of them has 12 in common. Is that all the information they use to get to this sentence? To get to this conclusion, that 0 and 1 have 12 in common? Maybe. I don't know. Like, I guess this does have to be true that there is at least one pair, because otherwise. This okay, yeah. So is that all the information you need to be able to juice everything? It's telling you it's a cube of 1,000 by 1,000 or something. Yeah. No, that's um each. What do you mean? Each scanner's visibility is like a cube of 2,000, technically 2001 by 2001, I think. Um, in the example, it's using scanner 0 as the base and rotating the others until they match. But this still comes back to the fact that they may not match at all. They could just. Okay, I mean, if we know that there definitely has to be one other scanner that has 12 in common with 0, then yeah, I guess that's true. We can if we know that for a fact, and that seems to be established, then yeah, we probably can. Big is the input anyway. So there's 27 scanners, and all we know is that at least one pair amongst these scanners have 12 in common. I maybe it's more than that. Maybe it's the case that every scanner has at least one other scanner that has 12 beacons in common with it. That allows us to start at 0. And then we have to figure out whether it's 1, 2, 3, or 4 that has 12 in common with it. And find the 12. So they're saying these are the 12. And that tells them where scanner 1 is. And then from 1 they're trying to find what overlaps with 1, and they're saying 4. And then that finds 4, and then from 4 or following this process. Okay, so it's not necessarily from 4. 2, they find that 2 is here, but we don't know which of the scanners 2 overlaps. They haven't said, but... So the 0 connects to 1, 1 connects to 4, and then 2 connects to one of those, 0, 1, or 4, and then 3 connects to one of all of those. That's the minimum amount that we can really deduce from this. Okay, fine. We can try and repeat that. So we can start at 0. We can assume that it has 12 in common with one of the other. Because once we have found that scanner 1 has 12 in common with scanner 0, then we can basically merge them together and say this is now just one big rectangle, one big cuboid with a list of beacons. Well, that actually makes it harder, because then it's a bigger set, and you're still sticking with 12 beacons, so that's probably not... You probably still want to keep them as separate sets. But just try and find 12 in common with 0 and something, or 12 in common with 1 and something. Alright, well, I mean, we could try and code a process that, given to lots of these, try and find if 12 of them match or not. Try and find if it's possible for 12 to match. And if the answer is yes, it's possible, we'll just assume, okay, then they match. Because in theory, it could be coincidence that 12 beacons just have the same distance pattern, but they don't actually coincide. But I guess we'll just have to assume that's so unlikely that it's not going to be the case in the input. And the facing and direction thing basically means that these columns can be swapped about, and the sign can be changed from positive to negative. So that's basically 6 permutations of columns times wait. They said there's 24 different orientations. it's not just all the permutations, because some of those are invalid, because it wouldn't have... It wouldn't... it has to be like orthogonal rotations or something. Um... So this is 2, 3, 4, 5 examples of orientations, but I guess there's actually 24 different possibilities. How do we get all 24? Do we just... So each of... Isn't there an algorithm for this? Cabsh? Oh, maybe I don't remember this stuff. We can't just do every possible permutation of columns and every possible positive or negative of each column, because that would be too many, wouldn't it? That would be like 48. Only half of those are valid. What's Cabsh? I don't think this doesn't. Oh, I see. P and Q, two sets containing n points. To find the transformation from Q to P. Both sets of coordinates must be translated first, so that their centroid coincides with the origin of the coordinate system. I don't know if we have enough information to be able to use this. Also, I don't really understand it, but I don't think we would need it though. The process of finding, if we restricted to just finding like 3 points that match and just assume that that's like likely the likelier subset of the 12, if they do match, then that's probably not too hard. So if we just like restrict to finding like 3 points such that their distance pattern matches, and then work from there, just continue to add a point every time it does. That would probably be the easier process. How many we got here? 1, 2, 3, 4, 5, 6, 7, 9, 10, 12, 13, 14, 15, 16, 17, 22, 23, 24, 25. So it'd be like 25, choose 3, 1,300. Okay. So if we would try every triplet, and for such a triplet, try every triplet in the other one. So we multiply those two together, so we're in the millions. And then for that pair of triplets, if we want to work out if they match, you have to do what exactly? You'd have to, if I wanted to work out if these three match these three, I would have to look at the interpoint distances, of which there are 1, 2, 3. And just see if that's a permutation of the other distances. Would that be enough? And if the answer is yes, then what? We'd have to try and build that up to 12. But okay, so at that point we would know. Man. About an hour in, I haven't started coding yet. Well, I can try doing that at the very least. Seeing how often that actually happens, that 3. Wait. Okay, but it's not enough to say... You've got to factor in... How many of your leaderboard friends finish this? What are we on? 19. 5 people. Well, I can start with that and see how often that actually happens, that 3 common to both. And then there's 27 scanners, so... Yeah, I think this might be one where I just have to just try a little bit here, and then I'll just have to think about it offline and try and understand the bloody description. Alright. This is part 1. This is crazy. This is literally the first time I can ever remember a problem where part 1 was just not... could not be comprehended. I still think it's just a really bad description. lack of mathematical language used. Which I know that he tries to avoid mathematical language, just so that people understand it. But this is a case where it would have made it clearer how to use mathematical language. I mean, I think it usually is clearer when you use mathematical language, but Alright, well, I'll just code something. Let's copy this in. At least pause the input. That's a start. Alright. Yeah, so these are in order, right? Okay, so then we could just... Alright, so let's just say... Okay. If not line dot strip then just skip that line. If line dot starts with Alright, just create a list called beacons. If line dot starts with that, then we just append what we have into the scanners. And then beacons is refreshed. Otherwise, we probably want to use... Do I want to use a pos class? The problem is the pos class specifies X, Y, and Z, and in this case it's actually indeterminate. Just put it as a triplet of numbers. Beacons dot and say tuple of comma It's all empty. What's going on? Line in f.read lines. here. So we've beacons.append tuple. Line.split. What's the problem? Also, I probably have to finish soon, so I don't think I'll really get any logic done. Okay, we've got beacons. Oh, whoops, that should be outside the... no. Yeah, but why is that one empty? Oh, I see. Oh, no, this is the wrong way around. Not gonna do the last one. I need to... Alright, just do it like this. If beacons is not none, put it on, and then the end of this process we'll just have to do alright, let's check we've got the right number. For I row in enumerate scanners print I row 0 to 27. What? That's too many, isn't it? Oh no, it does start at 0. Yeah, it does. Okay, good. Alright. So we parsed the input. There's nothing small I can do now. Like, if I do any logic, I'm gonna have to dive right in. I don't particularly want to. I need to finish soon. So, yeah, the idea was to find, like, triangles that match, and then build up from there. And the thing about the axes is confusing me, because I don't know exactly the process of all the rotations, but I'll just have to look it up. There's probably just a series of matrices you can multiply to get every possible valid rotation, because you can't just compute all permutations, because that will give you 48. That's twice as many as you need, so half of those don't respect the what's it called, the left-hand rule. So yeah, like yeah, and I can also probably offline. I could probably check the forums, see if anyone's actually explained this problem in plain English or mathematical English, because this, I still maintain, this is a terrible description. And I would say technically wrong, because I still think what I said about them being completely disjoint is technically true. Like, they could be. never did it actually say they have to have anything in common. They just said you're trying to find regions with overlap. But there's no reason why they would have overlap at all. I guess we just assume it does. Yeah, okay, fine. I'll just stop there. There's no point getting started with that yet. I was tempted to move on to another problem instead and come back to this one, but I'll try and do it in order. So that was 1 hour 20 minutes of reading part 1. Oh, what is part 2 going to be if this is part 1? If we're lucky, it might just be something that falls out quickly after solving part 1, because this is kind of crazy for a part 1 problem. Literally, I've never seen... I can't recall any problem of this nature where part 1 was just basically indecipherable. Alright. Well, see you next time.